we start?
3
3 more
more minutes.
minutes?
45.
45.
It's very sparse. Like, so can you please put in the we are starting? Then we will start running.
I'm not sure if they can run in 3 minutes. Anyway, I will start with some part which is not that crucial. So today what I want to do, there is one proof which may take like 1 hour to present. I want to show you, because also it interests several of you. So it is there is a nice argument which gives an approximation algorithm for distance d dominating set and distance d independent set using the recoloring numbers again. So the proof idea will be actually a little bit similar to what we saw yesterday. That proof for bounded neighborhood complexity or linear neighborhood complexity. I think this is a nice thing. So maybe that I will wait until everybody's there so that they can follow. And the other hour, which I will start now, and also in the end, maybe give you things which I did not have time to talk about in detail, so that if you want to explore more, and also that you have feeling of what's going on in this research area. Yeah, and also, if I can, I would like to very briefly mention how people are now extending this whole theory to dense graphs, because this is what's going on right now. In fact, I will also show you a couple of papers on archive. Like, since January, there have been maybe 4 or 5 extremely interesting papers which came out on archive. So some of them even last week. So it's quite exciting. It shows that this area is really lively at the moment. People are developing this theory. Start with so yeah, I'll start with something which is called low treewidth covering, which is kind of reminiscent to what Arminder told on planar graphs and graphs excluding a minor. He said that you remember maybe that he was layering the graph, planar graph, and then he was saying, look, if you take so you kind of number these layers, and if you take all the layers, let's say I modulo some number, you remove them, what you get, the rest is has bounded treewidth. So this is true for planar graphs. And then he said that, well, this is also true for graphs excluding minor, and actually something like that is also true for bounded expansion classes. And in fact, historically, this is what people were really interested in. So when Nechetil and Osona de Mendes, they introduced bounded expansion in one paper, which I think came out in 2005 in archive and then was published in 2008. And so they defined it using these shadow minors, as we have seen. But immediately in that paper itself, they said that, see, this is equivalent to having these low treewidth cover. And this is also equivalent to some other types of coverings. So I'll just define these things. So like this will, I will not go in depth. It's just for the culture itself, because it is historically this was the start of this theory, and I think it's still nice and it has good application. Although it seems nowadays that this weak coloring number has taken over, and this is kind of more powerful technique. I think these coloring numbers. But anyway, okay. So what we had, just to remind you. So it started kind of, so there were 2 things. I think I've seen maybe 2003, but I'm not sure. Says that if you have a planar graph, where it is D, then the treewidth, that's treewidth at most 3D plus D. you parameterize by solution size. If your graph has a large radius, you will find a long path, shortest path. But this shortest path will need a lot of vertices in the dominating set. So then that means if your radius is too big, you say no, I cannot get a dominating set of size at most k. So it means the radius is, let's say, at most k. But that implies the treewidth is small, and then you solve using B. Exactly. Exactly. It means these balls, radius, bounded radius, they have small. Linear graphs themselves have unbounded treewidth because of the grids, but the grids you see the unbounded radius. So this is a really nice one. And if you look at this diagram, there's a class called bounded local treewidth, which extends bounded treewidth, which they have this one. So this is, by the way, not true. I think for if I don't make a mistake, bounded expansion classes don't have this one. But they have the following one. So the corollary of this, and this was this layering Baker's technique, called Baker's technique, due to Brenda Baker. I think she developed this in the late 80s or something, to give some Theta's approximation algorithms for planar graphs, but this works for graphs of bounded local treewidth generally. So then, so this Hamilton explained it last week also. So if you have a planar graph G and an integer P, you can color any integer P. One can color vertices of your graph G with P plus 1 colors, such that for every I think most P colors, the subgraph induced by these I colors by any I color classes essentially, so what you have to do, you have to leave at least one color out, right? But then you have bounded treewidth. That's great.
Not a proper coloring, right?
In this case, it's not proper coloring. In fact, so if you take one color class, let's say I equals 1, what you get is a graph of treewidth 5. So if we wanted a proper coloring, we would need treewidth 0. If you could ensure that every color class, so if here it was I minus 1, I guess, instead of 3i plus 2, then you would actually get a proper coloring. Actually, I think we can get something like that.
But if it is not proper coloring, we can put lot of vertices in one color class, except say constant number of colors and vertices. Then
it should be true for any I color class. Right? So if you take this big color class, it will not have this proper coloring. I mean, if you just keep this big one. So essentially what it says is that any color class you remove, the rest has bounded treewidth. That's what it says, if you think of it. And this is also what Hamilton was explaining. How do you prove this? Well, you do this DFS, that's some vertex, and then you color, like 1, 2, 3, all these layers, you color them. And then, so up to P, and then once you reach P, we start at 1, 2, 3, etc. Okay. Now, any color class you remove, let's say you remove color class 3, it separates your graph into small pieces, and by this theorem here, this will have bounded treewidth. That's how it works. But this is specific to these planar graphs and also H minus. But actually,
why is it called bounded treewidth?
because locally you have not zero boundary. Locally means distance at most d. If you take a ball of radius d, boundary. That's what it's. That's why it's bounded locally. So treewidth in general is not bounded, but locally is not treewidth.
For that graph, treewidth is bounded, you are saying, bounded by 3d plus 2. As a function of d, you are saying d is 2 dots, d is 2.
Oh yes, sorry. Yeah, but because it has radius d.
As a function of d, that's why you are saying it's
The graph itself has radius d.
It has radius d, yes. So, okay, you can think of it differently. Take any planar graph. Take any subgraph of radius d. Like, take any ball of radius d. This is also planar. Now it has radius d. Now it has bounded d. That's why it's bounded local tree. Even if your original graph doesn't have radius, a small radius, you take a small radius part, it has bounded trees. That's what it is.
here, what about this proper coloring? By coloring, you mean proper coloring only?
No, any color.
So you have two adjacent buttons can have same color?
Yes? That's what I'm doing here, right? I'm giving, so, I mean, this was covered last week, so I don't want to go too much into detail. Hamlander explained it. So if you, basically, you take all the guys which are distance 1 of this particular vertex, you color them 1. Of course, they could be adjacent. Right? This could be a cycle. Could be a cycle, or what? And just like this, you could have, it is planar, of course, so, like this. What? It doesn't really matter. Anyway, look, I don't want to go too much into details. I don't want to spend too much time because the idea is just to give you hints. If you want to study more on your own, these things exist and you can go look for it. Okay, and well, this kind of colorings, we will call them low treewidth coloring. Now this works for these planars, but it turns out it also works for graph classes of Fourier expansion. In fact, you can characterize it. So this will give us a new characterization of expansion. So, but before that, let me quickly define some refinement of treewidth, which we call tree depth. Again, I will just define it so that I can explain it, so some of you might know it. What's the tree depth of a graph T? It is the smallest height of a tree T. Okay, so the height of tree being the, not the number of levels, but the number of edges when you root it. This has height equals to 2. Or do we take, maybe we take the, actually the number of edges. I'm not sure. No, tree depth 1, I think, are stars, so smallest heights of a tree T, such that G is a subgraph of the closure. Okay, what does it mean? I'll give you a picture. So this is your tree T. What's the closure of the tree? The closure of the tree is you put an edge between any vertex and its ancestors. Okay, this is the closure of that tree. So what I want to hide my graph inside this. So I want it to be a subgraph of this thing. For example, let's take. This, and then I have a triangle. So this graph G is a subgraph of the closure. This is the closure. forest means that, okay, there could be, several things, which each of them has a different. This is just to allow disconnected things. If it's connected, you take the definition I had before. So this is T1, T2. So the closure of the forest contains all edges between the vertex and its ancestors, and all its ancestors in its tree. Okay. Ancestors.
Is it kind of same thing of taking transitive closure?
Yeah, that's exactly the same. Closure, transitive, you can call it transitive closure.
So I guess we can bound tree depth by diameter of size.
Maybe, yeah, I mean, probably yes, because sure, if you graph this diameter d, that means you can take the path of length of diameter d, length d plus length d. That gives you a big peak, and well, maybe you do some branches like this, probably you can get.
If G is connected, then the number of vertices in this tree is same as the number of vertices in G, right?
No, G can have less vertices, C like this. 1, 2, 3, 4, 5, 6, 7, but here I have 1, 2, 3, 4, 5, 6, 7, 8, 9.
And G is sitting as a subgraph tree.
G is sitting, the green thing here, if you look, this is the green subgraph. Or,
Between two trees in a forest, you may not have any.
no. Yeah, this is just to accommodate disconnected graphs. It's just small technical conditions. Very often we talk about connected graphs and we just take a tree in the forest. I just want to be a bit more precise with this. If you want to talk about the tree depth, you should allow normally disconnected graphs, like treewidth, right? When we talk about treewidth, when we manipulate 3D compositions, we take connected trees, but of course you can do with a forest. Just do every tree independently. Okay? So,
Is it G subset of closure F, right?
G subset of, yeah, now it's a forest. Right. Okay, so for example, a graph of tree depth 0, no edges. Of tree depth 1, this is basically star forests. Right? Because when you take a graph of a tree depth 1 of height 1, it's just a star and there are no additional edges. The only thing you can do is a substar. I mean, you could have, of course, manipulate things like this. So this is tree depth 1, the star forest.
What is related to the tree width parameter?
I'll come to that. In fact, maybe I come to that exactly now. Observation. The tree width of G is at most the tree depth. So the tree depth is a refinement, you can see, of, say, of tree width. If you know you have tree width K, your tree depth might still be bigger. Why is that? Well, if you take your closure here, your forest. In fact, even better. Let me give you a whole chain of things. Vertex cover number of G. Tree depth of G. Close the path width of G. Close the tree width of G. I believe this is true.
tree depth is minimum among the heights of the.
Yes. Correct. What is this? This is the vertex cover number, smaller size on vertex cover. This is the tree depth. So path width we didn't mention in the lecture, but it was in one of the exercises. So it's like tree width, but you force your tree to be a path. Okay. So this is more restrictive. Oh, sorry, it's all the opposite. Tree width is the smallest, of course. The vertex cover is very large, so this is a set which, when you remove it, you have no edges. Path width, tree width, you know, and now tree depth I just introduced. So why is that? Let's see the first inequality. So a vertex cover, you have a small vertex cover, that means you have some set and everything else is an independent set. Then what do? Well, you can just, do the focus. So let's say this has size VC. You just take the path like this with VC vertices, and then you put lots of leaves for these guys. Let's call this I. Now what's the closure of this? The closure of this is just here you get a big clique. And these guys go upstairs. Of course this stays an independent set. But now you're completely free to put any edges that you had here, since this is a huge, everything is connected here. So the tree depth will be at most. So this is, the height is vertex cover minus 1 plus 1 vertex. Tree depth is at most vertex cover. So you can see that the path width is a refinement of tree width, the tree depth is a refinement of path width, we'll see that now, and the vertex cover is an even bigger refinement of tree depth. This, by the way, if you can find a vertex cover of the graph, this will give you a 3D composition. This can be useful sometimes. Any chain like that you can have. Okay. Why is the path width at most the tree depth? Well, you take the tree, well, the forest, let's take one component of the tree, what's going to be my path decomposition? Well, I'm going to use these branches. So remember, this is restricted, right? This is tree depth. So the number of vertices in each branch is tree depth plus 1. And my path decomposition is just going to be this as a bag, and then this one, and then this one. So this will be the first. So I'll put, for every leaf of my tree, I will put one node in my tree position. And then these will be the bags. First bag. Second bag. Third bag. And so on. The path decomposition. Remember what's the path width is the largest size of the bags minus 1. The bags are all have size 3 plus 1, so path width is at most 3.
Plus 1, why the plus 1 thing?
This is the number of vertices. The height was the number of edges, so number of vertices. Alright, and then, well, for path width and tree width, it's trivial because path decomposition obviously is a tree. So I'm not detailing that.
But the back size is like.
Tree width plus 1. Because this, I'm 1 and -1, which is true. Okay, anyway, this is all not that important, it just allows me to state. I just want to state this characterization. And if you're interested in these things, I'm just giving the definition so that you can explore more on your own. This will not be part of the exam. You can stop listening. Okay, some definition, and then I can state that characterization of Courcelle and Courcelle and Mendes. So what's a p-treedepth coloring? It's kind of what I said for the treewidth coloring. P-treedepth coloring. Okay, is a coloring. I'm not putting a bound on the number of colors. It's a coloring of G. But this time it will be a proper word. But this will follow from, I think, the definition, hopefully, of G such that for every I most P, any I color classes induce a subgraph of treedepth. And you see here, that's why in the treedepth definition I need to allow disconnected things, because I want to allow disconnected subtypes. Notice that for or is it diagonals? What? So I'm not completely sure about the canonical definition. But essentially what I would like is that for one color class I get an independent set.
So it's a p+1 coloring?
No, the number of colors can be arbitrary.
Okay.
But you're fixing, this property should be for P.
Okay, okay.
So for I equals 1, it should give me things of treedepth 0. So I guess it's -1. Well, see, I'm not completely sure. So I didn't go too much into details, because I don't want to go too much into details in class. I just want to show you that this exists, so that you can perhaps can use it for you to know this. Okay. You can have the same notion for treewidth. So these things are called low treedepth colorings or low treewidth colorings. It's a coloring of G. Same thing, but with treewidth now. And finally, there is another notion of colorings. It's called a p-centered coloring. In fact, what they will show is that on bounded expansion graph classes, these things are all equal in some sense. I mean, up to constant. G such that for every connected third notion of coloring is a bit strange. P-centered coloring. It's coloring of your graph. So if you take any connected subgraph of G, either it receives a lot of colors, strictly more than P. If it has a few colors, then one of these colors appears exactly once. Notice that these three definitions imply that you have a proper coloring. Because here, if you take a connected subgraph of size 1, it can receive only one color. What I'm saying, of size 2, so you take an edge basically. It cannot receive a lot of colors because they're just two vertices. But then one of the colors should appear just once, exactly once. So that means the two endpoints of the edge receive different colors. So this in particular implies it's a proper color. And these also become treewidth 0 and treewidth 0 means independent size. It doesn't matter if you don't catch the definitions. It takes maybe some time, and I don't want to give too many examples. I don't want to use this too much. I just want to state this nice characterization, which is the following. Maybe no. Just one small remark. For those of you who like colorings, remark that this definition and this definition generalizes two important types of coloring, which are called acyclic coloring and star coloring. So this, so for P equals to 2. So for P equals 1, it's just a proper coloring. But for P equals 2, this one will be, I think, star coloring, because that means any two color classes have treewidth 1, which is collection of stars. So this is called a star coloring, if you know about that. And this one is called acyclic coloring. Acyclic coloring means it's a proper coloring, and any two color classes induce a forest. So these are nice generalizations of star colorings and acyclic colorings, which have been studied a lot since the 1980s. I mean, this even before this was introduced in the 1980s. This probably in the 60s. So these are studied on their own, but they're also studied a lot to give bounds for other things. So you'll see many papers where they want to define some notion of coloring, and they use acyclic coloring as a method to give bounds on that strange coloring that they're defining. So it's kind of nice for people who do coloring that this theory embeds them in a sense. Also definition trail and Patrice Hernandez, also nicknamed Pom. Patrice Hernandez. So in 2005, I mean, the paper was published in 2008, I think. What they proved is the following. Let's see the class of graphs. And then another characterization which involves all these notions. The following and equivalent. C has bounded expansion. There's this function f1. not so many colors. So this time I'm bounding the colors, but it's some function of p. This is the same as having bounded expansion. That's what they showed. In particular, it implies, p treewidth covering, because bounded tree depth implies bounded treewidth. But actually, this is also equivalent. So you can rewrite this as bounded tree depth. Even though this is weaker, it's still characterization. Finally, these p set of coverings also. All of these things are equivalent.
For that coloring, distributed coloring, can I color all the vertices differently than distributed coloring?
Yeah.
Mod is
Yes, because every color class will have one, so this will be, of course, always. Well, I don't know these colors too well. I have not studied them. Just wanted to mention. I didn't think too much about them because I've never worked with them, and since I didn't really prepare anything for this class, so just want to state the dimensions. In fact, I mean, nowadays, I think people really mention these treewidth colorings because this is probably the strongest of these properties. I mean, even though they're all equivalent on bounded expansion. But you can really work well with this one, especially for, we saw, Hamid showed you that these things have algorithmic applications. You have this Baker's technique, which gives you approximation algorithms. You have this, he showed an FPT algorithm for subgraph isomorphism. So exactly what he showed would work here. Exactly the same thing. So you take your subgraph H, your graph H, which you want to check if it is there and has a copy in your graph G, and you'll basically color you'll color, but you will fix P as to be probably the number of vertices in H, plus 1 maybe, something like that. Just number of vertices of H. And then you know that any copy of H couldn't use more than, P plus 1 colors. And this gives you an FPT algorithm. So this works also for exactly the same algorithm works for K. So these things all have very nice algorithmic applications. And then, why not working with treedepth, right? Because treedepth is so much stronger than treewidth. So we might as well use treedepth rather than treewidth. In particular, there are some problems which are solvable on bounded treedepth, but not on bounded treewidth in FPT time. So why not use treedepth? It's stronger. And if you have bounded treedepth, you have bounded treewidth. So as I said historically in that paper, when they introduced boundary expansion, they showed this theorem. And later, Juling Zhu came up with this other characterization using the coloring numbers. And nowadays, if you look at, for example, if you look at the lecture notes given by the Philip Chuk brothers, they show this using the coloring numbers. So I think they show this characterization using the coloring numbers. So you can now, I think these coloring numbers are a nice tool, and you can derive everything using these guys, using these notions, instead of going through the shadow minors and doing these colors. But this can be very useful, of course, in some applications. not like it's useless. Depends on what you want to do, right? And exactly for these efforts, for these algorithmic techniques, this is very useful. Okay. So we have now seen, I think, 4 equivalent definitions of normally expansional. The shadow minors, then we did the covering numbers, then we did the neighborhood complexity, and now these low tree depth coverings and so on. So 4 equivalent things. So it really shows that, you want to work with boundary expansion, choose any of these 4, whatever suits you best, and work with that. It's really powerful, really nice. And actually there are more tools even, which I can maybe mention briefly at the end of the but I'm not sure if they give characterizations. There are more properties which are very nice, which can also be very helpful. Okay. But now maybe I want to go to maybe the last technical topic, let's say, of this lecture series, which is another nice application on these distance D dominating sets and distance D independent sets. And what we'll show is we'll show that there is some kind of so there is a nice, packing and covering duality between the two. And in fact, as you will see, there will be nice bounds which control them with each other. If we have, so now we will use the coloring numbers again, and this will give us this theorem. So maybe I can state the theorem. Define what I want to talk about. So distance D dominating set. G. This is D of vertices. Such that every vertex is D dominated, which means it's a distance advocacy from somebody in D. So it's like the normal dominating set, but instead of distance 1, we will all know distance D. So if you take D equals 1, it is exactly the dominating set. And we have the corresponding notion of a distance D independent set. Distance D independent set. So I will deviate a little bit from the notation which is used in the literature in this thing because I'm more used to this one. So for me, distance D independent set means that any 2 vertices are distance at least D apart from each other. G is a set I for independent set of vertices of G such that any 2 vertices in I have distance at least D. So if you think of a normal independent set, it means D equals 2. Because everybody has distance at least. So if you look at the paper where this theorem is from, or the lecture notes from the lecture brothers, they use strictly bigger than D. I don't find it that natural, so I'll try this one, because I'm used to this one. Of course it's equivalent, but it could be confusing if you look at the literature. example, a path. The path has a large tree depth. The path of length n will have tree depth log n. So all these inequalities are strict. I mean, what I showed you. There's no bound for the other side. No constant for it. Remarks. Another remark is what? Maybe if you let me define the dominating D of G to be the size of the smallest D dominating set. And then D of G to be size of the largest independent set. So observe the following. If you have an independent set at distance d, let's say 2d plus 1. So if you know you have an independent set where so everybody has a distance at least 2d plus 1. This is my independent set. If you take one vertex in your dominating set, now you are looking for this is an independent set. Distance d plus 1. You're looking for a dominating set. Well, a vertex of your dominating set can dominate just one of them. Right? Because if you draw the things which are distant, this is a ball of radius d. If you want to dominate this vertex, you have to be inside that place. But then you will have distance at least d plus 1 to this one, so you cannot dominate. So that means any dominating set at distance d is at least the size of an independent set of 2d plus 1. So if you take dominating set of size 1, the normal dominating sets, it's at least the size of an independent set at distance 3. Which is sometimes called packing or packing. I think somebody talked about this, no? Maybe too young. So this is so these notions are like dual in this sense. So this is classic, packing and covering duality, which is very much studied in optimization and in particular using linear programming in optimization. So in these kind of things, when you have these kind of bounds, it's very nice if you could also find a bound for the other side. So the question is, can you find here some upper bound where you get a function of this one? Remember that for the strong and weak coloring numbers, we have this kind of relationship. Right? This is very nice because it basically tells us you can bound it one, you can bound the other. Right? Because that means you can replicate the bound here, and also this one will be squeezed in between some function of the dominating and some other dominating parameter. And well, I think this is not true in general, but for bounding expansion classes, it will be true. There will be something like that. And this function will in fact be a constant. Well, not really a constant, it will be just something which doesn't depend on the number itself, it will just depend on d. And it will in fact be be something which depends on the recoloring number. So we will take recoloring number to the square, and this will be your factor. So this is what I would like to show you. This theorem was proved by Courcelle. And I will check the so this funny R is pronounced G, if I'm not mistaken. It's Courcelle. Wait, I'm sure I pronounced it incorrectly. Something like that. So what did he say? He said that, look, if you have a G, and you have a recoloring sequence for 2D plus 1, then you can use this to build a dominating set and an independent set. I will give the precise numbers like this, and the independent set is not too large compared to the dominating set. So, G and another sigma, where the weak coloring number of this graph in the sigma is at most, at distance 2D plus 1, is at most some constant C. There is an algorithm, a polytype algorithm, and the algorithm is quite simple. It's kind of a greedy algorithm. Building, what does it build? A D-dominating set of G, called D, a 2D plus 2 independent set of G, let's call it I, such that, so we know that we have this. I'll just put it in the chain of inequalities. Size of D will be at most C squared is I, C squared. So actually, it's slightly even stronger. Not only gives me an independent set at distance 2D plus 1. No, he gives me one at distance 2D plus 2, which is even stronger because the vertices are even a little bit more powerful. So we'll take the sequence, we'll use similar kind of arguments as we used yesterday, look at the weak reachability, we take the minimum, these kind of things. This will give us a dominating set, an independent set, and this gives a good approximation, because it's a polynomial time. Why? Because this dominating set is sandwiched between the independence number and the C squared times the independence number. And we can construct these two sets. So what does it mean? Okay, we need the coloring part, the sequence, the colored sequence. But we have seen before that if you have a graph class of finite expansion, you can build these things efficiently. So as a corollary, you get that. If C has finite expansion, one gets if D is constant, it's a constant. Because we know the recoloring number, the C in a boundary class of boundary expansion will depend on D. Note one thing, I just want to remark that in general this is not true. In fact, this D dominating set, the independent set, if you want to, well, I don't know if it's true. Yeah, I don't think it's true in general, but also, even for graph classes of one expansion, you can't compute them in FPT time, for example. So there is, in fact, I think the problem is, for those who know parameterized complexity, this is W1 hard, parameterized by the feedback vertex set. For graphs of bounded treewidth, you will not get FPT for treewidth if D is part of the input. So if D is not constant, and you want to exactly compute one of these things, the independent set or the dominating set, D could be something which depends on n, the number of vertices. You cannot do this in FPT time when the parameter is the treewidth, for example. So it is much like you cannot get good algorithms exactly, even on very special classes of bounded expansion like treewidth, bounded treewidth. This doesn't exist. But you have this nice f of D approximation algorithm, which is quite amazing. So f of D approximation algorithm means that the solution you get is, for dominating set, is at most f of D larger than the optimal. And for the independent set, it's at least, let's say 1 divided by f of D times the optimum size. So it's not too much away. I mean, and this f of D is really the C squared, where C is the recoloring number. So maybe I show you the algorithm, and then we have a small break. And after that I'll prove it to you. Prove the correctness. So what's the algorithm? So G and sigma is given. I'll start with an empty dominating set. Oh, but by the way, just a remark that if you don't like algorithms, this is also important for people who don't like algorithms, but they like to study these notions because, of course, this shows a combinatorial bound dependency between the two, which is also very nice for people who like structural studies of graphs. So this is not just applied to algorithms. It's nice also in the structural world of graph theory to have this kind of dependency systems. So we'll start with A to be an empty set, and R to be all the vertices. What are these three things? For this. So we'll construct this algorithm. There's a bullet time algorithm, so I'm describing the algorithm. And then I'll prove it to you after the break. So we'll construct D, and we'll construct I. Okay, now D will be just this D, so this will be the D dominating set. This A will not be I, it will be a candidate set where we'll find I inside that. So we'll find our I inside this A. And this is just a working set where with the currently undominated vertices. This will be, we'll stop when this is reaching empty set. Undominated.
We are building both together.
Sorry?
We are building both together.
Yeah. I mean, in fact, what I'll do, I'll build D and A, and from A then there will be another algorithm to find A, to find I. first step is to build these three things. While R, so while there are undominated vertices, while R is an empty, what do we do? Select smallest vertex of R. When I say smallest, as usual now, I think you're getting used to it, I take smallest in sigma. With respect to ordering sigma, which was part of the input. Let's select the smallest.
Sigma is any ordering?
Any ordering. But the approximation factor will come from the weak ordering number of this ordering. So of course I want a good one for the weak ordering number of this ordering, which I can get, remember, for graphs of bounded limits. So select smallest vertex U of R. Let's do my ordering sigma. I add U to A, so that means this U could potentially will be in the independent set. Perhaps it will be in the independent set. And to D I add a lot of things, because I want it to be a dominating set, so I add all these weak reachability of 2D plus 1 of this U, which was the smallest in my R. So I add all of this to D. The idea is that let's hope that this will dominate the whole lot of vertices by doing this. Of course, this is not that big in the sense it only depends on, this is basically at most C. Number of vertices. Some constant. Okay. By the way, just a remark how to compute this. You can just do a BFS. After you have the ordering, you can cut here and see what can you reach here and so on. Start to and whenever you reach these guys, so you do a BFS at with 2D plus 1, but you can never use these guys. So you remove all of these guys. I mean this is not accurate, but you cannot do this. Whenever you do this, you stop. Anyway, it's just a side remark. You can actually compute this in polynomial time. It's not that. And then what we do, now we update our R, because now we have selected all these guys in the dominating set, so we need to remove from R everybody who is dominating. Update R, that is, R becomes R minus this thing. A distance. So everybody who has a distance at most D from some vertex inside capital D. So these are the dominating vertices. I remove them from my undominated vertices. So that is my first phase of the algorithm, which computes. So my dominating set is computed like that. My independent set is not yet complete, but I have computed a candidate set, which is all these minimums of the weak reachability set. So after I finish, I have no more undominated vertices, so it's clear that this is a D-dominated set. D is a D-dominating set, this is clear, because I'm just defining greedily this algorithm. And what we have also is we have that.
You also need to remove R,
inside the dominating set.
Yeah.
So obviously he's dominated. So U will be automatically dominated, removed in this step. Okay, let me maybe precise the outlook so that you understand what's going on. What am I doing? So I'm working with this ordering, right? Sigma. This is how I represent my graph. And I have some set of already dominating vertices. Looks like this. This is the dominating vertices. Inside this, of course, I have a dominating set. This is D. Everything else is in R. And inside my D, I have my A. So my A is some vertices of D.
What is it? A.
This is A. A is very small, and you see what's going on because we select a vertex, U, we put it in A, and then we put all the reachable vertices, which are reachable from U, inside D. In particular, we put U inside D also. Right. So this A is really small, it is this green set. My D is a bit bigger, and the dominating vertices of D are the white vertices here, they're even bigger. That's what's going on. Everything else is R. Everything else is R, so all these parts here are undominated. What am I doing in the next step? In the next step, I'm selecting the minimum vertex U of R. It is this guy. This is my next U. And I'm doing all this business again. I put it inside A. He becomes green. It's in A. I look at the weak reachability. Well, my picture is not so nice because oh no, it's fine. In fact, this is the minimum in R. I look at the weak reachability set of U, and I put it inside D. D is perfect. So what's the weak reachability set? It's something which is, so this guy goes to D for sure, and maybe something here. So everything which is reachable here. No, it means that there's a path length that moves to D plus 1, or I can go like this. So this I add to the dominating set. So it could be that I'm adding things which were already inside, which were already dominated, doesn't matter. But now I have at least, I'm sure that I have enlarged my my A and my D by at least this U. Because this was in R. So it was neither in D nor in A. So I've at least added one more vertex. And now, of course, it may dominate a bit more here. And of course, the edges here are completely arbitrary. Okay. And like this, you go on and you grow. This is what's happening. U is this smallest vertex U. So at each step, we select a new U. What is it? The smallest undominated. So this was undominated. And it was the smallest undominated with respect to the ordering. This U I added to the dominating set. I added to the set A, potential independent set. And then I not just add U to the dominating set, but also all its weak reachability set. So some things which are to the left of it, I also add. So note that this weak, except for this guy, except for U, everything actually was already dominated, which I added. But I'm hoping that like this, I will dominate even further at distance D. So my R will definitely get much smaller. Something smaller. At least by one it gets smaller.
But all vertices left to U is already dominated.
They're already dominated, but they might be very useful to dominate other things. Taking them. And this algorithm is finite because at each step I select one undominated vertex at least. So there's at most n number of steps, where n is the number. So it's a polynomial term algorithm. And it is correct in the sense that it creates a dominating set, which is good. notice that this dominating set is at most C times the size of A. Why? Because at each step I select one guy, I put it in A, and the C weak reachable vertices I put them in D. So that means I have put at most C times the number of vertices in A inside my D. So this is my first, this is a good inequality N. And so maybe this is so I didn't give you the second phase of the algorithm will be the construction of I. Then I'll prove to you the bounds. But maybe let's have a break. 5 minutes. You can reflect on the algorithm. Let's start at 3 plus 10. It is 3 to 10. 3 plus 10 always.
IIT Ropar. Darshan, is Darshan around? Your Darshan. What is your institute? Goa campus. Gopika Govind, are you around?
She just left.
Okay. Where?
I think so far.
No, so some of them did not mention their affiliation in the registration. It's just India. So the registration fee, sorry, certificate. Okay, I will ask. Harsh Gupta from ISER. Ravindra Mohan Bedi. You are Ravindra. So how do you write INFC? C is small? Right?
Yes.
Like IISC.
Yes.
And Pragya Arora? Then Raina Mary Thomas. He was here. Big school. Yeah, that is okay. Ravina Pilani. Rudra Prasad Tarai. তুমি কি করছো? তুমি যা কিছু পাইছো না। Yeah, I also don't. Maybe it's extra. I forgot to do. If he comes asking for a certificate, please. Saraswati, IIT Gandhinagar. And Shakil is not around. He is from CMI, but should I write CMI or Chennai Mathematical Institute?
CMI.
I know, but should I write in the certificate? CMI?
Write the full name, no?
Not for
Ah,
everything.
yeah, for IIT maybe no one.
Yeah. Also INSC,
Let's see here.
No, CMI is okay. Shubham?
Yes, sir.
And Siddhant Nayak, it's one. And Subhashachi Chatterjee,
He's from IMS.
sure. Pratik Sarkar,
He's from IT.
no, I don't check the official Guwahati has a lot of one name is Pritesh Kumar and Sushanda Roy, I think is from Gopika Govind, we don't know yet.
Polarity. Polarity is pretty important. For the boundary. For the polarity is not. Then you need terrible. Okay, so we have our algorithm. Let's restart. Well, to finish both the algorithm, because the algorithm is not finished, since we are still to build a set I, and we still need to prove the bounds. Let me see what we do. So what we'll do is we will take A, and inside we'll kind of find our I. And this will be based on the following thing. So I will not prove the claim at first, I will explain the claim, deduce the proof, and then I will prove the claim. So the claim is, for every vertex of A, there are at C minus 1 vertices of A. So other vertices of A, there is at most C minus 1, such that B is smaller than A in the sigma ordering, and they are close. So remember that my goal is to construct a set I, where everybody is a distance at least 2d plus 2. Not 2d plus 1. I'm doing it because we'll get it kind of for free, so we are doing this. So I'm claiming if you have your vertex that you have selected in A, so in my picture it was the green set, right? So there's, so this A, I mean this is what I call U, right, in my algorithm. So my algorithm is like this, it will take a U, do all this business, then it will take the next U, take the next U, take the next U, and so on. This is how we construct our set capital A. We add U to A and then like this. And at each step, this is the smallest and dominating vertex. So now I'm looking at all these B's, which come before A, so that means they have been selected before by the algorithm, right? And I'm saying, there are not so many, I mean among those, there are not so many which are close, which are distance at most 2d plus 1. So maybe this is at most 2d plus 1, and maybe this, but most of them are not a distance at most 2d plus 1. Most, yes. And that at most is this C minus 1. Deducing that, I mean, assuming that, assuming the thing, what do? You greedily select vertices of A in I. What does it mean? Take the first one, you put it in I. Okay, then the next one, maybe it is too close to this one, so you don't take it. And as long as you are too close to somebody you already selected, you don't take them. But whenever you get the vertex which you could put in the infinite set, you do it.
So distance is less than or greater than 2d plus 1? Distance AB?
So what I'm saying is, whenever I look at the vertex here, among all of those which are before, there's not too many which are distance at most 2d plus 1. At most, that means most of them will be a distance at least 2d plus 1. So that means when you're here, so I can't pick this, I can't pick this, there's at most C minus 1 I cannot pick at this stage. But this guy I can pick, right? Because, yes. Wait a minute, it's the other way around. Yes. No, I'm confused. My picture is kind of the other way around.
Should DB theoretically put there?
No, no. So, do I go? Maybe I need to go from right to left. Yeah, I guess you go from right to left, I guess, right? You go from here, go from the last one. Say AK, you pick it, and now you know that there's at most C minus 1 which are smaller, which are too close to A. Yeah, I think it's this way you have to do. So you forbid the C minus 1 on them. I mean, let's make it smaller. The C minus 1 you cannot take. But the next one, this is fine. Pick it. So this gives you an infinite set. I think this is correct. Maybe one needs to double check. But the idea is this. And then what I'm saying is that the I have selected now is at least A divided by C. Because when I pick one, I kill C minus 1 plus 1. So pick one, I forbid C, I remove C from my potential set, and then I reiterate. So it's a greedy procedure. And this is, if we have this, we are good because that finishes the algorithm, because now we have, by this inequality, you have D at most CA, but we also have A, which is at most CI. Yes, so that you get C squared I, right? So you get that. D is at most C squared I, which is exactly what I wanted to do. And this is a distance 2D plus 2 independent. Of course. Okay? So this is the description of my algorithm. There are these two phases. First I build D and this A. And from the A, I can show that I don't have to remove too much. Like at most, C minus 1 by C proportion. But at least 1 over C proportion I can take in my independent set. This is a 2D plus 2. So that's the
How did you get B less than CA?
This is because when you look at the initial algorithm, when you pick somebody in A, how many, at the same time you're also enriching your D. But your D you're enriching by this set, right? But we know this is the weak reachable vertices from U. So by our assumption, it is at most C. It's a set of size at most C. Because the weak tolerating number at 2D plus 1 of any vertex is at most C. So whenever I put one vertex in A, I put at most C vertices in D. Okay, so it shows that D is not more than C times A. And then from this set A, I'm picking at least 1 over C vertices to get I. So that means D is at most C squared I. You get this. So these are the two steps of the problem. So now it just remains to prove the claim, right? It just remains to prove the claim. And you will see that the arguments are, it will ring a bell, it will look a little bit like what we did yesterday. So by the way, there is a much simpler algorithm, just for the, which gives an approximation for the dominating set, which I put, it was in the tutorial number 9, I guess. I think after you see this, you can try to solve that algorithm. It's easier than this, much easier. Ideas are a bit similar. I should do the proof. Maybe I keep the algorithm. Let's erase the theorem then. Proof of claim. So you look at your A, and let's look at the B that you have selected before. Okay, I want to say that, and let's assume that the distance between them is small. Because I want to say that there are not so many B's which have this property. So there is a path, since they are not too far from each other, there is a path going to D plus 1 at most, which can be anything. It's not a weakly reachable path, it can be anything. Like that, for example. But what I know, it's called P. Length of P, I assume it to be at most 2D plus 1. I want to find some properties of this path to show later that I cannot be. In fact, I will show that there are not too many B's like that. Okay, let's decompose the path into 2. And what are we doing? As usual, similar trick, as usual. Let's look at the minimum which is this, okay? P is PA concatenated with PB. Okay, so notice that this NAB, it belongs to the weak reachability set. Again, you know, same trick as usual. It is the minimum, so it will belong to all these weak reachability sets. I mean, for B and D. Reachability 2D plus 1 of B, and also of A. Why? Because you know there is a path. Of course, this PB is smaller than 2D plus 1 because it's a subpath of P, which itself is smaller than 2D plus 1. So there is a path, and this guy is a minimum, so we are not using anything on the left. It is fulfilling the definition of weak reachability.
So PA is definitely the smallest part, what is PA? Any path?
No, PA is the subpath of PB. P, sorry. So PA is this. PA is the path P from A to the minimum. Okay?
So you may use the minimum of the path from A to B.
Yeah, it's the minimum of the ordering sigma. I'm always representing, this is always the same picture, this is my sigma. I'm ordering the vertices. I have no idea how the edges look like. I just draw my graph like this from left to right, and I put the edges, how they are.
So a minimum of all the paths or some path?
Some path. You can take the minimum. You know that there is one which is at most 2D plus 1. You take that one. Any. If you want to take the minimum, it doesn't really matter. If you take the minimum in particular, yeah. You know it will be a vector at most 2D plus 1. By my assumption. My assumption is I want to study these kind of vectors. So I'm assuming this. If there is no such vertex, I'm happy. I want to show that there are not too many. If there is one, it looks like this. Okay, and this I go from M and B to B. This is the subpath. This one. Okay, I cut my path into two. Alright. Okay, now I want to say that the length of this PA should not be too small. So this is also in weak reachability. Right, this is kind of trivial because it's the minimum in sparse, this part that length must be this one. So I want to claim that the length of PA is at most D, so as at least D plus 1, PA. What is that?
Otherwise, when we entered the dominating set, we could have covered A as well.
When we enter the dominating set.
Well, like since we removed the neighborhood of
Yes,
yeah, from R.
correct. Exactly. So we know that we are processing these vertices from left to right. Because we are always choosing U as the smallest. That means that B has been added to D before A. So we start, the algorithm was like this, was designed like this, that we first put B inside A and D. And now what we do, we add to D the weak reachability set of U. That means that this is in D. And this is in A and it's also in D. At this step where we have put this in A, we have put this in D. But this guy was still undominated because I was able to select it later. So that means this path cannot be at most D. If it was at most D, he would have been in this set, the dominated vertices, and I would have removed him from R. that indeed implies that this path is not at most d, so it's at least d plus 1. Okay? Just by observing what happens in the algorithm. But that means the other path is really short. I mean, really, it's exaggerated, but it's at most d. Right? Because the whole thing is at most 2d plus 1. If one side is at least d plus 1, or the other has to be at most d. Okay. So now, okay, that's the situation. Okay, I have this. I want to show, to tell that there are not so many b's. Let's assume there were, in fact, I will show you that there is only one b. Like that. What do I mean by one b? What I mean is that there is only one b who shares this minimum. So now I will show that. For every a, the set of b's such that b is smaller than a, distance exactly these b's that are defined, and this NAB for every a, for every x. NAB is equal to x. What I'm writing in mathematical style here is that, so I fix my a, I take some x, this x will be this MAB, and I'm saying there's only one x like that, which will be MAB for some reason. So the set of b's, which are smaller than a, whose distance is most 2d plus 1 to a, and that share the same minimum, okay, here, the x, this isn't 1 at most. So to show this, this is easy. So suppose there are two, you know. So if there was another one, let's see b prime here. So that means, you know, there would be a path prime whose minimum is the same. And it looks like this. This is p prime. But I know that they intersect at this minimum, and this is the minimum of both paths. So I'm assuming by contradiction that this set is at least 2. So that means I have my b and my b prime, which have the same minimum. But then same argument as before. Because of this. We know that this path is small between this and b prime. This is at most d. That's why I proved it before. So it means when I included this guy in, I know this guy is in the denominator set. This was in A. Well, I should have removed this b prime at this stage. I should have removed him. Why? Because he's already dominated by this one. So he should have not been a candidate in A. So he doesn't exist. That's why it is. So between b and b prime, only the smallest one can exist. This is not a real vertex. This is not that. Okay? This is just because of this property. But if you had one b prime which had the same properties as b, again you would, I mean, I'm not going too much into details, but you would have another p prime going from a to d to d prime, sorry. You can decompose it into 2 by exactly the same arguments. You would show that the path from the minimum towards this b prime would be at most d, which means that after the algorithm has processed b, it would have removed b prime from the set of candidates, which is a contradiction because we assumed that he was picked in A, right? I mean, our assumption was that this guy is in A. Did I write this? Yes. I think this is not possible. So this is true. Okay. How do we conclude from that? Well, we are done because what we have shown is that the set of these vertices here, all these b's here, for every possible minimum of the path, there's at most 1, but this minimum, remember, belongs to reachability set of A. So, there cannot be, this set is bounded by C. So So there cannot be too many minimums. There can be at most C possible minimums. Each of them gives you one other guy in B. So that means there is at most C. Well, C minus 1 because A is itself in this reachability set. So there is at most C minus 1. Okay. Let's write it this. At most W reach of 2D plus 1 minus 1. Vertices V and A. This implies this, that the number of the vertices V with these properties, which are in the claim, is at most the weak reachability set, size minus 1, because we are not counting A. And why is that? Because for each of them you will find some minimum. They are not. Each minimum is in this reachability set, so that's the number of possible minima. And each minimum gives you one B at most. So you don't have too many B's. And I guess this finishes the proof. Full proof, because I showed you that using the claim now we can get the proof is complete. So I think it's quite a beautiful technique. So of course you have to be a bit clever on how to choosing these numbers for the reachability set. And then the arguments are, you see it's always a bit the same trick. You look at the minimum, try to find some tricks to bound some number of vertices. It really looks a bit like what we did yesterday for the neighborhood complexity. Okay. Well, I hope you at least got kind of the flavor of this. As I said, I repeat again, in the tutorial there is a much simpler version of it, which works for the dominating set, which is still pretty nice. You can use this to get it. Are there any questions? So I think this is the last technical thing I wanted to show you. So, and maybe now for the last end of the course, I will kind of continue hinting to other directions and maybe make sense of it now. I think now we have all the tools to understand this picture a bit better. And I will maybe talk to you about some very recent developments, which I don't know well myself, but they seem quite exciting.
Could you tell me where the treewidth of path is logging?
This is an exercise. So this is a classic thing. So you will find this in the book of Session-1 and Courcelle. You can find it also in the lecture notes by the Philippe two brothers. Session-1 and Courcelle.
Sparse.
And the sparsity is. So, but even better, I think there is a nice proof of in the lecture notes of the sparsity series by Michel and Marcin Filichuk. I think the link to these is given in one of the solutions to the tutorials. I gave the links. So they have they did this course a couple of times. I don't know if they're still doing it, but at least they put online 3 years in a row, like 2017, 2018, 2019, something like that. 2020, I don't know. And so there are these three. So I think the last one is nice. You can get the last version of the lecture notes, but the videos are from I think 2019. They're still also very nice. And you also have some exercises, tutorials. So some of our exercises are taken from them, so thanks to them a lot. They didn't have the solutions. I mean, they have solutions for some more complicated exercises, which I didn't take. just again just mention some things very vaguely, just to tell you that these things exist. If you want to dig more and you're interested in the topic, you can read about these things. One thing which I've seen which is used is the notion of, sparse neighborhood covers. So if C has bounded expansion, so I'm not going to define this maybe globally. Every graph G in C has a sparse neighborhood cover, and this can be very useful in some applications. Again, I'm not sure if this is a characterization of it, but at least I've seen that they have this property. So what is this? This is a family of clusters of G. Let's say C1 to CK. And such that what? So for every vertex in the graph, and for every, when D is fixed, there exists a cluster which contains your neighborhood at distance D. So imagine that you have a collection of these, you can kind of cover your graph here with these clusters. Now, any vertex you want of your graph should be entirely contained in one of the clusters, meaning its neighborhood at distance D. Okay. No, it didn't. But there are more conditions. So also you want that every vertex of V is not in too many clusters. But there's some function of the clusters. So that basically means that these clusters don't overlap too much, too many times. Essentially that's it. Maybe there are some other properties, so don't take this for granted. I think there's another property which they call bounded degree, but I forgot what it means. But what they show is that for every graph class of bounded expansion you can get these objects, and this is used to get algorithms. I think it's used for the next thing which I'm going to mention just briefly, which is that. You remember that I told you about this Courcelle's theorem for bounded treewidth, which meant that every property you can do in monadic second order logic, you can write, you will find an FPT algorithm for the FPT for treewidth. So what you get is a linear time algorithm to check this property if your graph has bounded treewidth. So there is a similar theorem for first order logic, so a simpler logic, but for your graph classes of bounded expansion. And I think they use this kind of. They use a lot of things, but this is one of these.
If you have a single cluster, this satisfied, right?
Yeah, so that's why there are more conditions. Sorry, no, I didn't take enough notes. I looked at it yesterday, but I think there is a. Maybe the size of C is bounded. Sorry, yeah. My notes it was a bit late yesterday. My notes are not good enough. theorem. Okay, I don't know about the boundary expansion one, but so for every first order property, P, graph property. So what means first order? First order means you have your vertices of your graph, you can have them as variables, and you can quantify them. You can say there exists x1 for all x2, this kind of thing. But you can't quantify over sets. If you quantify over sets, that would be second order. Like monadic second order. So this is simple, first order. But for example, you can express, I think you can express the monadic set in this language. First, P. And monotone graph class C. So P and reject linear time. If C has boundary extension. So that means you will have some function of the class and your property B times that. So this is a very strong property, which is another success story of these bounded expansion graph classes. You take any graph class of bounded expansion, you take any first order property, graph property. Now for any graph, you can check if, well, I didn't check for G in linear time. If G is in your class, you can check it in linear time if your class has boundary expansion. Linear time meaning, okay, there is a huge function which will depend obviously on the class. It will basically depend on this expansion function and your property. So I don't know much about this. I just know it exists, and so this is a very powerful, strong result, which analyzes many things. Where before it was known for planar graphs and for H-3 graphs, and then it was limited to boundary expansion. And in fact, it was also so for no events it also works. So this is by result by Grover, Kreutzer, and Sieberts, 2017. So it's almost true in the sense that instead of n, you will have for more dense classes, we get a f of the class and the property times n to the 1 plus epsilon. Running time. This is for all epsilon. Choose an epsilon. You can be as close as in some sense you can be as close as linear as you want. You cannot be linear. Okay, so this is for no dense classes. And by the way, this is for monotone. So this works for no dense classes, but for monotone no dense classes, they actually prove that this is a if and only if. In the sense that take a monotone graph class. Monotone means you can delete anything. You're still in the class. Then every first order property, you will have this kind of running time, if and only if the class was no index. This is extremely strong. So it kind of closes the game for monotone graph classes, for the people who are looking at these kind of meta theorems. So this is quite nice. And now, now there is ongoing work to generalize this to any class, and especially hereditary graph classes. So hereditary are less permissive because you don't, or they are less permissive or more permissive. I mean, you don't necessarily allow to be stable by removing edges. You only require that you're stable by deleting vertices. So this is what hereditary graph classes are. So this works only if your graph class is monotone, so this is a stronger property.
No evidence.
Yes, no evidence. So I'm not going to into details, but I just want to state these things to show you that they exist, and that this is very deep results in which have an association between the algorithms. In fact, they use a lot of logic. I think of course, it's first order logic. Right? So they use tools from logic. They use tools from these sparse graphs, algorithmic tools. They use these kind of things also. Many properties they use to prove these kind of theorems. And so by the way, now people are trying to do this for dense graph classes. And what they're conjecturing, so maybe you've heard of this click-width. Click-width is a kind of an extension of tree-width, you could say, which allows also dense graphs. So bounded tree-width graphs are always sparse, because they're tree-width degenerate. But if you study bounded click-widths, you will immediately see that you allow to have large peaks, any large peaks. But this Courcelle theorem works in a certain way for certain formulas. It also works for bounded click-width. So you also have this kind of results for dense graphs. Now this has recently been extended for first order logic also, for first order properties. It was extended to graphs of bounded twin width, which is more general than click width. Okay, so I'm not defining twin width, but it's like in the last 5 years it was studied, and it's a very powerful technique again. So in twin width what you do is you contract vertices, not necessarily adjacent. And what you do is you look at how their neighborhood differs. So if you have two vertices like this, they might. So you will contract them into a single vertex, UV. And what you do is you look at what was in common. Maybe this was in common, you're happy with it. And what was not in common, so those are the ones which are seen only by you and by me. You contract here, you put them as red. This is now a single vertex. And in twin width, you do this operation, and you want to bound. Your graph has bounded twin width. If you can do this by bounding the maximum degree in the red graph. This would be an entire lecture series on its own if you wanted to study that. But the nice thing is that these also produce very dense classes, but it also contains sparse graphs like H-line of free graphs. It contains. If you have bounded twin width, if you exclude a graph as linear, you have bounded twin width. If you have bounded click width, you have bounded twin width. So I put this in the diagram here. If you have bounded twin width, you have bounded DC dimension. And it was proved by the colleagues who introduced this. So this was Stéphane Thomasé, Rémi Vatrigan, and Andrew Kim. French colleagues, they introduced this in 2020. And they proved this kind of theorem for these graphs also. But now you have dense graphs. So the question is that people are trying to solve now, very passionately, is that what are exactly the dense graphs for which we can have this kind of theorems? And what the conjecture is that those are the graphs with which you take your sparse graphs, you take your graph of bounded expansion, you take your lower dense graphs, you perform certain logic operations on them. So it can give you dense graphs because you can create large peaks, but in some sense they come from the sparse graphs. So there's inherent structure, there's a sparse graph to which you have done some modifications. And then they show that if you have this property, you also can solve your problems, in linear time or polynomial time, first order problems. Now the challenge and the conjecture they have is that this is essentially a characterization. There are no other graph classes, hereditary graph classes, which are like that. And this is going on at the moment, and actually just last Tuesday there was a paper on array, which maybe I can show you. I wanted to show you the things which happened kind of during this course. How do I switch on? Can you help me? So roughly during this course, so in January, there was a super nice paper by Zieberts, so the same Zieberts here, who is an expert on these coloring numbers. So he wrote a survey, basically, which he has put on archive in January. So this actually helped me a lot to prepare the part on colorings, weak colorings.
Who wrote that theorem? For every FO graph, there is Courcelle?
No, actually I don't know. This part I know is this, but probably this boundary expansion was proved before. Unfortunately, I didn't get that. Survey by Zieberts. You can see it was uploaded in January on the generalized coloring numbers. So it was a great source for me to prepare the lecture, of course, on the coloring numbers. So it's a big survey of 64 pages. And he also mentions a lot on these bounded expansion classes, not just the coloring numbers. So this is quite nice. Okay, this is another kind of survey, I think. 16 pages by Michel Felichuk. So, and this addresses what I just said, that you take your kind of sparse graphs and you apply some logic operations. You get what they call structurally sparse graphs. Okay. So if you see the summary, you get treewidth. There's a dense analog of treewidth called shrub depth. You get these pathways, treewidth, and so on. Minor free classes, twin width, I told about, boundary expansion and lower dense. So these are the things. And then these are these new concepts where you have these structurally sparse graphs, monadic stability, monadic dependence. So this uses what they call model theory. These kind of nice diagrams. So the things we talked about in this lecture are on the left side here, you see. Bounded tree depth, bounded pathway, bounded tree width, minor free. Okay, this I didn't talk about. Bounded expansion, lower dense. And now you can apply your operators, these logical operators, to get more complicated classes. So that's what they call structurally bounded tree depth, structurally bounded path width, structurally bounded tree width, and so on. And then on the right you get these dense graph classes. Bounded click width, bounded twin width. Okay, bounded flip width. This is interesting. So 2 years ago there was a paper on archive by Simon Torunchik, who's another colleague from Warsaw. So the Warsaw team is really on the front for this. And he introduced this parameter, and for those of you who like games, it is actually defined like it's a cops and robber game. This flip width was defined as a cops and robber game. And by the way, he conjectures that this is equivalent to what I said, that the graph classes for which first order logic is tractable. There is this conjecture, which is the model. Monadically dependent. Anyway, so these are things I don't understand, but I know they are there.
Would you show the diagram?
So this is, you see, also January 25, so it was uploaded in January. Unfortunately, it was a bit too quick because last week 81 pages. So this is the last version, but he uploaded 2 years ago. Last year I put one of these things, and then he has this kind of diagram also. This is bounded treewidth. These are the things he talked about. Yeah. Bounded flip width. So this is nice for monotone graph classes. This is nice for hereditary graph classes. These dense ones. Okay. All right, and then last Tuesday, he and Jan Dreyer uploaded this little shorter 48 pages paper where he introduced merge width. And this is another width parameter which generalizes twin width. I mean, I haven't had the time to look at it, but I just saw it passing on archive. And now we get this diagram, similar diagram, but now he says that this merge width might be more interesting. So bounded merge width implies bounded flip width, but so this flip width is defined using a game, and this is more combinatorial. You merge parts of your graph like that. I think he conjectures in the paper that they are equivalent, in the sense that if one is bounded, if the other is bounded, if your graph is hereditary, maybe. So this is a brand new concept. You get this nice picture of how they merge vertices to define this parameter. Also, almost 2 weeks ago, I just saw this paper, which defines shallow brambles. So they are trying to, you remember the brambles from treewidth? So they are, I didn't read the paper, but it seems that they are defining, what could be brambles for the shallow language. So this might be an interesting read. So you see how fast these things are developing, right? Just in 2-3 months now, you had all these papers related to this. So what I showed you is kind of a crystallization of things which happened in the last 10-15 years. But the field is now evolving towards dense graphs, as you can see, and it is very active, very, very beautiful things. That's what I wanted to show you. How do I?
No, just is your laptop working? You can see the screen in your laptop.
Yes. Oh, I want to shut it down.
Ah, okay.
How do I move it?
Yeah.
There was a
Remote.
remote, no? So this just to show you the things in the field. And maybe now we can go to finalize, I think. Maybe explain you the picture. I think now we have many definitions we can work with for this picture. So as we saw, I mean, these very simple graphs, you have these paths, or path forest. These are among the simplest ones. Of course, they are included in the class of forests. Right? You have, well, we can also put star forest now. We have seen that they in particular have bounded tree depth. Okay. Star forests. We had the bounded vertex cover number. So this had bounded tree depth. We just saw this morning. Okay, then you have the bounded path width. Here you have bounded tree width, and I will have enough space. Right? bounded path width is bounded tree width. Sparse bounded tree width. Okay, if you want some specific graph classes, you have plane graphs, which are nice as well. They also have bounded tree width. And those we have worked with in the first tutorial. Question about them. This in fact K493. We also saw that. So these are in particular, this is the same as two trees, partial two trees. So I think in the first tutorial we showed that these guys are partial two trees, and I think Shagnik showed that partial two trees is the same as K493 graphs. Okay, and they are planar. Right? Planar upon the genus. That we also saw in the lecture. Now we have excluding a minor. Maybe that we didn't see, but when you bound the genus, you actually exclude some minor. Okay. This is stronger than excluding a topological minor or excluded subdivision. Right? We have also talked about it. When you have a bounded degree, well, you certainly exclude some complete graph as a topological minor. Of course, path forests have bounded degree. Well, maybe I will miss some of the edges, but that's not a problem. Okay, then we saw bounded expansion classes, right? So they are sitting here. We saw it this week. Okay, we saw that they have bounded degeneracy. Mentioned all these classes at some point or another. So this is nice. You have a nice hierarchy of graph classes here, right? That you can. There is some. These tree widths, of course, they exclude the minor. Okay, so you have this. Okay, what about bounded local tree widths? Okay, so the nice thing is now you have these local things, right? So bounded tree widths, we saw bounded local tree width. Of course, graphs of bounded tree width have it, and we saw Harmander showed that when you exclude a minor, you have this property also. Local tree width. Oh, sorry, do you have it? Maybe you have to exclude a certain minor. Not sure about this one. But definitely bounded genus they have it. And actually, so this we haven't seen, but you can define the local versions of these things. So now you've understood this locality thing, is that you look at a bounded radius subgraph, and you will have a property in that. So in the same way you could define locally excluded minors. Locally excluded minor. Okay. Okay, this of course generalizes excluded minor. And in fact, this is very interesting. These bounded local tree width graphs, they are not necessarily bounded expansion. But there will be no elements. Even though they look very structured, if I'm not mistaken, they don't have necessarily bounded expansion. And you can actually define locally bounded expansion. Locally bounded expansion, which generalizes bounded expansion. So it means that, you know, for every D, you take a subgraph of your graph of bounded expansion, of a class of bounded expansion. Of your class. For every D, you take a subgraph of your class, of radius D. class of these kind of subgraphs should have bounded expansion. This is what it says. So it's a little bit more general. Then you have your no dense graphs. Now I'm running out of space. No dense. And of course, yeah. So bounded expansion, locally bounded expansion. No dense are here. And what we saw is that, in fact, there was a bounded declic number, you remember? So this was, I showed you, I gave you an argument that if you had bounded expansion, you certainly had bounded degeneracy. In fact, the argument was showing that if you have bounded degeneracy, you have bounded declic number. And this no dense graph also has bounded declic number. Yeah. So this declic number is quite interesting. And this bounds the VC dimension. So I also mentioned the VC dimension yesterday, 2 days ago. This sits very, very far on the top. So it's much more permissive. It allows much more things. It's quite an interesting thing. This VC dimension, you can, if you can work with the VC dimension, you will work with all these graph classes in some sense. If you bound your VC dimension still, all of these graph classes have bounded VC dimension. So that's interesting. Yeah, and then and then you have these things I just showed you on the method. So then you have the dense ones. So there your typical basic graph classes are cographs. So this we didn't mention at all. For cographs, you have the version on the truth which shows bounded click width. Okay, this has been generalized, as I said, as bounded twin width. Nice, which this one actually got things excluded minors. And these are all also have bounded VC dimension. And of course now here you can insert all these flip width merge widths and these new interesting graph classes that are interesting members. But I don't know more about them. Yeah. The star forests are actually cographs also. Bounded degree doesn't have bounded degree width. Okay, there are probably more connections, but you figure out. Alright, I don't want to bore you more, but this is maybe a global picture that you can now have a little bit, you have an idea about the connections between these graph classes. So it's a very rich world of sparse graphs that we have just started touching in these 2 weeks. And you saw it was already a lot of things. Yeah, so I guess I'll finish the lecture. Okay. Thank you. Any questions on this last? So bounded maximum degree is equivalent to bounded degeneracy. Right? We saw that it's a factor 2 away, right? Bounded max, right? It's the same as bounded.
Can you add the links to those archive papers on the WhatsApp group?
Sorry?
Those archive papers that you showed us.
Yes.
Could you just mention maybe the authors or the things on the WhatsApp group?
Sure, I could give the links.
Yeah.
Sure. I'll do that.